For physics by myself, Montefilis Benavides. So, for the introduction, the purpose was to analyze the motion of a spring mass system that was like oscillating due to the spring, but was also like released not from the vertical, which meant that it was swinging around as well. So it was at an angle. So I released it so that it would swing and begin oscillating up and down, while also side to side. And really, we're looking at Newton's second law and the energy principles here to use as our foundation. So the real data that we used was using tracker analysis, and then the theoretical simulation was just using the GlowScript models. And pretty much you're just looking at the mass's motion to see change in energy and see if it follows the energy principle. So the physics explained. Pretty much the force of gravity here, just like always, is mg since we're on the planet Earth. The net force is the change in momentum over the change in time. We have the spring and gravity forces acting here, which meant that the net force was the force of the spring plus the force of gravity, which then we can change the force of the spring into negative k multiplied by the vector L minus L naught, and then all that multiplied by L hat plus mg y hat. And so the change in energy here is just the work done by the surroundings plus q. And since there's no q that we're going to be accounting for, we're just looking at the work done, which is just delta k plus, well, change in kinetic energy plus the potential energy of the spring and the potential energy of gravity, which all equals 0 because there's no change in energy. And there's some other formulas right here for K, UG, and US. So the assumptions of the model. So the model, the mass that was used was 0.402 kilograms. And the video that was taken was pretty much just like a side angle showing that there's no change in Z, just the X and Y position vectors. Now the length of the actual like spring, we measured to be 0.7 meters. So the initial conditions, we released it from rest, so it was at 0 meters per second velocity, and the position vector, as you can see below. The system here was the mass spring Earth system with nothing being the surroundings. Tracker data pretty much just showed the X and Y positions over time here. So when we used the first 9 seconds, we were solving for the oscillation period, which would be 2 multiplied by pi multiplied by the square root of m over k. And we found that to be 1.51964 seconds. And solving for the spring constant, that was just 4 times pi squared times m over t squared, or the period squared, which equaled 6.8751 newtons per meter. The relaxed length, using the equation, we found to be 0.12697 meters. GlowScript code, pretty much I needed to go in and just change a lot of different things. So that just meant me putting in all the like initial conditions and like being able to calculate all the different things that we just talked about in regards to like energy and all that. So the conclusion, pretty much when we look at it, show that there were similarities and differences between the observed and predicted graphs, as always. However, the motion was generally the same. The energy did seem to be conserved, which is what we wanted to see, just because we're assuming that there's no outside work being done on the system. So this is consistent with what we were expecting. Possible errors, however, were misclicking on the tracker data, because when I needed to actually like click on the center of mass every time, I could have misclicked it. And then negligible forces, like say drag or like some sort of wind that could have been in the room, could have, meant that the system wasn't actually fully isolated, and therefore there was work acting on it from outside the system. So that's also something that wasn't accounted for. And what does it mean? Finally, pretty much So for the model system, was the energy principle satisfied? Yes. In the graph right here, you can see that there was no change in energy of the system. Like there wasn't any recorded external forces acting upon it, which meant that if you summed up the gravitational potential energy, the spring potential energy, kinetic energy, if you summed everything up, you would get a constant energy. There was no change in energy whatsoever, which is what we like to see. And then two separate estimates for the oscillation periods for X and Y. Here in the X direction, we had three different oscillation periods that I found, and then we just take the average to find the average period for both the X and Y. So for X, I said that was 1.652 seconds, and for Y, that was 1.5194 seconds. Thank you.